How you doing? I'm Mr. Rose, and today we're going to have a kind of total review of electric force and electric field. To do that, we're going to start with two charges, say Q and Q. This small q has a massive small m, big Q has a massive big M. Now I know that depending on the charges that I associate to small q and big Q, I have two options. Those two charges are either going to come together because of an electric force that brings them together, or they're going to be repelled because of an electric force that repels them based on the charges we associate with small q and big Q. Now we know because of Newton's laws that those forces have to be equal and opposite, which is why I have my arrows pointing or my vectors pointing the same way or in opposite directions. And we know that that can be brought to us by Coulomb's law, 1 over 4 pi epsilon naught, Q1 times Q2 over r squared. This is a vector, so I have it in my vector notation times r hat. Now, charge is a property of matter just like mass is a property of matter. And we know that every mass has a gravitational field associated with it. We just tend not to talk about it. Every charge also has an electric field associated to it. So we want to know, what does the electric field do to these charges? To do that, I'm going to sub in a 1, a unit charge of 1 for big Q here, and just see what happens. So I'm going to sub in my 1 into Coulomb's law. So I have 1 over 4 pi epsilon naught. Remember, epsilon naught is the permittivity of free space. We can summarize that as just a K, our electrostatic constant, but we keep it in this form kind of just for historical reasons. Also, as we get further on, it becomes a little bit easier. Q times 1 is just Q over r squared, and we're left with this new equation, which seemed kind of straightforward. 1 over 4 pi epsilon naught, again, that's just my constant, times Q over r squared. Again, my electric field is a vector, and this is very similar to if we made a comparison again to our gravitational field. Here we feel on Earth a gravitational field because of our big mass of Earth. We never really talk about it, we know it's there. This is the same thing where I associate this large Q having an electric field. This is the electric field that will be observed by small q. So here I have two pictures again, depending on my charge of Q. I either have an electric field that's pointing towards my charge of Q, or an electric field that's pointing away from my charge of Q. Now, how do we know what direction my electric fields are? My electric fields I have drawn over here, just two very simple examples. I have an electric field of a positive and a negative. This could be a positive charge and a negative charge. This could also be a dipole, which we'll talk about in the next lecture. And you see my electric field lines going from positive to negative. The way we think of an electric field is the motion of a positive test charge. So if I take a positive test charge and I put it right there, it would be repelled away due to the positive nature of that charge. Same thing on this negative nature of this charge. My positive test charge would come and be attracted to it. Here I have a uniform electric field because I have a whole bunch of positive on one side, a whole bunch of negative on one side. We sum all of that up, and I know if I put a positive test charge anywhere into that field, it would get pushed down to the negative plate. It doesn't matter where, it's repelled by a whole lot and where it's close. It's attracted by a big force when it's close to the negative side. So the electric field and the electric force inside that is uniform. To combine or compare my electric field and my electric force, let's come back over here. Remember, electric field is 1 over 4 pi epsilon naught, Q over r squared, my r hat, which means I could find my electric force in either of these two situations or any situation is the electric field that's associated with it times that charge Q or that charge Q, or if I have a charge Q there. It is always the strength of my electric field times the charge it's acting on it. Again, just like a gravitational force, it is due to a large mass, like, say, the Earth, and then the acceleration of gravity, F equals ma. Here we have a very similar equation, but it is our electric force equation. An electric force is a Newton per Coulomb. That's our SI unit. And because it is a vector, it does, just like force, obey all vector laws. So here's an example. We have 4 charges, Q1, Q2, Q3, and Q4. I've color-coded my reds are positives, my blues are negative. They're all separated by some distance a. What we want to know is, what is the net electric field inside of all 4 in the center of this imaginary square? Well, here I have our charges of positive 10 and negative 20 newtons per Coulomb, respectively. Our A we set as a distance of 5 centimeters apart. A could be anything. We're just using 5 centimeters for this example. From inspection, because of my given conditions, I know that the magnitude of the electric field from 1 is equal to the magnitude of my electric field from 4. I can say the same thing for the electric field of 2 compared to electric field of 3. I take that and I plug it into my newfound electric field equation of 1 over 4 pi epsilon naught q over r squared. Remember, we can only examine the electric field and the electric force charges of specific items. So I'm looking at the field due to Q1, the field due to Q2. Then I'm going to obey the law of superposition, means I can add them all together. So plugging in just for my electric field of 1, or the electric field from Q1, 1 over 4 pi epsilon naught, 10 nanocoulombs is 10 times 10 to the negative 9th, separated by some distance and through the magic of editing. We have my electric field is 1 over 4 pi epsilon naught q over r squared. Now I'm looking to the electric field at E1, or from the charge of E1. So I have my electric field is 1 over 4 pi epsilon naught times 10 nanocoulombs, which is 10 times 10 to the negative 9th, divided by my r. Now my distance r we know is the square root of a over 2. I'm sorry, a over the square root of 2 from Pythagorean theorem. So my distance r is 5 times 10 to the negative 2, 5 centimeters over root 2. I get the electric field due to charge 1 of 7.2 times 10 to the 4th newtons per coulomb. I then know that my electric field at E4, because they're the same magnitude, opposite direction, negative 7.2 times 10 to the negative 4th newtons per coulomb. I go through the same derivation for E3 and E2. I come up with E3 is 1.44 times 10 to the 5th newtons per coulomb. E2 is negative 1.44 times 10 to the 5th newtons per coulomb. And then underneath that, I have drawn, I put them next to each other, at least I attempted to, my electric field vectors. And I can see from inspection that E2 is bigger than E4. I can see by inspection that E3 is larger than E1. So I know my net field is going to be up in this positive quadrant direction, probably in the straight up direction, but I'm not sure. How do I find out exactly what it is? I have to go to my vector notation. So vector notation, I wanted that in IJK notation. So here I have the electric field of 3, 1. After I subtract them out, is 7.2 times 10 to the 4th, as we see, 7.2 times 10 to the 4th, times cosine of 45 in my negative I hat, plus 7.2 times 10 to the 4th, times sine of 45 in my positive j hat direction. I do the same thing for the electric field of 2, 4. After I subtract E24, I get 7.2 times 10 to the 4th newtons per coulomb. So 7.2 times 10 to the 4th cosine 45 in my positive I hat. Same thing, 7.2 times sine of 45 in my positive j hat. Negative I plus positive I, same magnitude, comes out to 0 I hat. 7.2, 7.2, sine 45, sine 45, both in the j hat direction, means I have 2 times that in the j hat direction, which means my net electric field in the center of this picture, due to those 4 electric charges, is just 1.02 times 10 to the 5th in the j hat direction, and that is newtons per coulomb. These should actually be swapped. Newtons per coulomb in the j hat direction. Well, again, since we obey the law of superposition, what if I don't have 1, 2, 3, 4 points? What if I have a distribution of points? Like if I have some rod of length L, I give it a negative charge, just arbitrary negative charge, and I want to know what is that electric field at some distance P away. I'm sorry, at point P, some distance A away. Well, we've done these before in Newtonian mechanics. We've done this once already with an electric force. We're going to follow the same protocol. I know that if I have a charge distribution, this is a linear charge distribution, I can call that lambda, is my charge per unit length. We've done this. Here's another example. We've done this before. I could have a charge per unit area. I could have a charge per unit volume, just like a mass distribution of a mass per unit length or a mass per unit volume. So if I know lambda is Q over L, I know that a very small piece of charge, dQ, at some small, very small piece of length, say dr, I can say dq is my lambda, my charge per unit length, times that small length dr. Now I'm going to plug that into my electric field equation, just like we've done before. electric field is 1 over 4 pi epsilon naught Q over R squared. Well, I know my electric field at point P due to this whole thing is, if I sum up all the electric fields, my law of superposition, which is an antiderivative or an integral. So I'm going to go from a distance A to A plus L. A plus L times the antiderivative, my constant, for 1 over 4 pi epsilon naught, lambda dr over R squared. I know that 1 over 4 pi epsilon naught, lambda are constants. That comes out. I'm left with the antiderivative. I want to keep going here. I'm left with the antiderivative of a whole bunch of constants, 1 over 4 pi epsilon naught times lambda, of 1 over R squared dr, which after we equate, we have an electric field from this line distribution at some arbitrary distance A away of 1 over 4 pi epsilon naught times lambda of 1 over A minus 1 over A plus L. Uniform electric field undergoing the law of superposition. Thanks for watching. I'm Mr. Rose. Please like, comment, click, subscribe. I do that well for other classes, not for you. See you next time.